So everybody done quiz 2? Yes, this is another problem sheet. Again for tomorrow. So tomorrow we will do two problem sheets. Tomorrow we have two problem sheets. Okay. All right, guys. Good afternoon. Listen, guys. Make sure you sign the attendance sheet. If you haven't, if you come late, could you please sign the attendance sheet? Yeah. Okay. So last week, just to summarize, last week we started talking about portfolio theory, and portfolio is as I explained. Listen, guys. Portfolio is a collection of investments. So these are two examples. The notation n denotes the number of investments. X1 to Xn denote the losses in the n investments, right? And there are 6 cases. There are 6 cases to consider. These are the 6 cases we need to consider, right? So case 1 is where the losses are IID and the number of investments is fixed. Case 2 is where the losses are IID and the number of investments is a random variable, and so on. So last week we did the first 3 cases, cases 1, 2, and 3. So this week we're going to do the last 3 cases, 4, 5, and 6, right? So we will start with case number 4, which is where the losses are I and ID, which means they're independent but not identically distributed, and n is a random variable, right? And then we will move on. Okay. All right. All right. So once again, remember there are 3 variables of interest: the total portfolio loss, the minimum portfolio loss, and the maximum portfolio loss, right? Okay, so let's leave it here. Can you see what? Let me check. All right, so let me start with case number 4. So case 4 is where case 4 is where the losses are INID and the number of investments is remember you, right? So the first thing we need to do, we need to look at each of these three guys, okay? So let's start with A. So we want to find the CDF of the total portfolio loss, which is denoted by S, right? Okay, and this is you can write this like this because of what? This step is known as the total probability rule. I mentioned this many times last week. This is the total probability rule. Okay. Now what you have inside is the conditional probability multiplied by the probability that capital N equal to little n. Now this conditional probability is the same as what is in case 3. Remember, you may remember this from last week. This is case 3. We did this last week, right? In case 3, the expression that we got for the CDF of S is this one. This is based on the fact that the number of investments is a fixed number, right? So therefore, the conditional probability here is the same as this expression here. Okay? So what I'm going to do is I'm going to replace the conditional probability by this expression. Okay? So this is what you will get. And you multiply this by the probability that capital N equal to little n. Okay? Are you guys with me? And this is similar to what I did last week, you may remember. So the PDF of S is simply the derivative of the CDF, so it will be okay, just the derivative of this. So you see what I've done here. Let me explain one more time. The conditional probability that S given any is the conditional probability term is precisely equal to the CDF that we got in case 3. Because in case 3 we were assuming that the number of investments is a fixed number. Right? So therefore you can replace this by this. This is what we got. This is the expression that we got for the CDF of S under case 3. Yeah? That's what I have done. Is that clear, guys? Or no? You guys okay? Yeah, okay. If anything not clear, just please let me know, guys. I really want to help you. Okay. So that's A. So let me put this back here. Now I'm going to move on to part B. All right, B. We want to find the CDF of U. Okay, and this is equal to the sum from 1 to infinity. Okay, once again, this follows by the total probability rule. This is so by the total probability rule. Okay, now this conditional probability, the conditional probability of U given n equal to n is equal to what we did in last week for case 3. Remember, this is what we did last week. You may recall this is the expression that we got. This is what we got for the CDF of U when the number of investments is fixed, right? So what I'm going to do is I'm going to replace the conditional probability by this expression here. Okay, you see what I've done? I used the result from last week for case 3. So I replaced the conditional probability by the expression that we got for the CDF of U last week. Okay. Now you have two terms here. The first term is the sum of this, which is 1. So this can be written as 1 minus the sum okay. So this is the expression for the CDF of S. So CDF of U for case 4, right? Okay. Any questions? Please let me know. Then the PDF of U is simply the derivative of this, right, with respect to U. So if you differentiate this with respect to U, this is what you will get. Once again, I'm going to use the product rule. Oh my, sorry. I'm going to use the product rule. this is what you will get. So the result I have used to get this is the so basically I have, if you differentiate this with respect to u using the product rule, this is what you will get. Okay. Alright, so it's just the product rule for, I use the product rule for the product of n functions. Right. Okay. Any questions so far? You okay? Let me know, guys, if anything not clear. Let me know. Okay. All right, please. All right. Okay. Next, that's B. The next thing I'm gonna do is C. Right, is the CF of V. The CF of V is this, right? And once again, using the total probability rule, this you can write as like this, all right? Just using the total probability rule. Okay, now if you look at this conditional probability, this is precisely what we got for the CDF of V under case 3 last week. So if you look at what we did last week, this is the expression that we got. This is the expression that we got for the CDF of V when n was fixed. So the conditional probability is the same as this, right? Okay, so you can say that this is equal to it's equal to this. Yeah. Alright, so that's the CDF of V. Now the PDF of V is this, yeah. So you differentiate this expression with respect to V. So once again, I'm going to use the product rule to differentiate this. So this is what you will get the following. You will get this is what you will get. So what I have used here is the product rule for differentiation of, it's the rule for differentiating product of n functions. So this is okay. Any questions so far? Okay. Yeah. You guys sure? Yeah, everything okay so far? Right. Today I forgot to bring chocolates. I will bring it tomorrow. Today I forgot about chocolate. No chocolates here. Don't be angry with me. I will remember to bring tomorrow. All right. Any questions, guys? You sure? No. All right, guys. So I will leave it here. Let me pull this out. You don't need this. Let me see if I can do some examples. You don't need this. Okay. Okay, I decided not to do some examples at the moment. So now, we are done with case 4. So we've got 2 cases remaining, case 5 and case 6. And those are a little bit tricky because for case 5 and case 6, you need to know, have you guys done multivariate distributions before? No? I'm coming, guys. Don't, why you say no all the time? Eh? You haven't done multivariate distributions before? Yes? Yes or no? No. Okay. Anyway, the thing is, to do case 5 and case 6, you need to know about, you need to know a little bit about multivariate distributions. So before I do them, I need to give you an introduction to multivariate. Before I do those, let me see if I can. Maybe what I will do is, okay. So before this, I need to introduce you guys to some stuff about so let's say preliminaries, I need to introduce you to some stuff about preliminaries on, right? Because without this, I don't think you'll be able to understand what I will talk about later for case 5 and case 6, right? Okay, now suppose I mean, let's start with the bivariate case. In the bivariate case, you have two random variables coupled together, right? And you say that they have a joint distribution with the CDF fx1, x2. What does that mean? It means right? This means that the joint CDF is defined as the probability that the variable x1 is less than equal to x1, little x1, and the probability that capital X, the variable x2, is less than equal to little x2. So this is the definition. This is the definition of the joint CDF, right? Okay. Now, I mean, you've probably seen this before. Had you not seen this before or not? Yes? No? Oh, come on, guys. Talk to me. The marginal CDFs, when I say marginals, I mean the marginal CDFs. The marginal CDFs for x1, to obtain the marginal CDF, all you have to do is you have to put so to obtain the marginal CDF of x1, you just put x2 equal to infinity. Alright, and that will give you the probability that x1 is less than equal to x1, right? And similarly, to obtain the marginal CDF of x2, you put x1 equal to infinity, right? And that will give you the probability that x2 is less than equal to x2. So these are known as these two are known as the marginal CDFs, or marginal distribution functions, right? And they are obtained from the joint CDF by putting either x1 or x2 equal to plus infinity, right? Okay. And there is also something known as the joint survival function of x1, x2 is defined like this. And it's the probability that x1 is greater than x1 and x2 is greater than x2. So this is whenever you put a bar, whenever you have a bar in front of on top of f, what that means is it's a joint survival function. There is a survival function. So and it's defined as this, right? So this is a counterpart of the joint CDF, where joint CDF is always defined as something less than or equal to, whereas survival function is defined as something greater than. You see the difference between the two, right? So right, let me finish writing it, then I will explain. Don't be confused. Right, so what I have written here, guys, the joint CDF can also, the marginal CDFs can also be obtained from F bar using these formulas. I hope you understand what the marginal CDF of x1 is 1 minus this, which is 1 minus this guy here. If you put minus infinity for x2, this probability is the same as this. Do you understand or not? No, some of you look blank. Do you follow what I'm saying? Yes, no. Because if you put x2, when I put minus infinity here, this takes minus infinity. Anything is greater than minus infinity. So this disappears. Right? So what you have is simply the probability that x1 is greater than x1. And 1 minus this is simply the CDF of x1. Right? And similarly, the CDF of x2, the marginal CDF of x2, can be obtained by taking 1 minus this. Just think about it. I know I don't know if you are not used to multivariate distribution, this may be a little difficult. But I hope. How you sir? Do you follow what I'm talking about or no?
Yeah.
You do?
Mm-hmm.
Maybe you have done this. Had you guys done multivariate before or no? All of you? No? Come on, guys. do you guys follow this or not? How are you, sir? I ignore you.
Fine.
You're fine? What about you guys here? Do you follow this or not? You do? You guys? Okay, alright. Okay, good. So let me put this here. And also one more thing I want to say. Any questions you guys have, just you can email me or come and see me or Zoom me anytime. All right, so don't be afraid to see me. Okay. And one other thing is this. the marginal survival functions, sorry, the marginal survival functions are as follows. So this is the joint survival function, this one here. To get the marginal survival function, all you have to do is just put so the marginal survival function for x1 is obtained from this by putting x2 equal to minus infinity, right? And the marginal survival function for x2 is obtained from this by putting x1 equal to minus infinity. Okay. So these are so there are a few things to note here. We have the joint CDF, we have the joint survival function, and we have the marginal CDFs and the marginal survival functions, right? Okay. There are relationships between f and f bar. In fact, if you know the f, you can obtain the f bar, and the other way around, as I will explain in a minute, right? So, for example, f bar is equal to 1 minus okay. Okay, this is one relationship. So what this relationship says is that if you know the marginal CDFs and the joint CDF, then you know how to compute the joint survival function, right? You might have seen this before, I don't know, right? And also the reverse is also true. You should know so the second relationship says the following, that if you know the joint survival function and the marginal survival functions, then we can obtain the joint CDF. So these are two reciprocal relationships, right? So both of them are useful. right, in certain situations. It can be proved, but I don't expect you to know the proof of this. I don't expect you to, I mean, it's not really hard to prove these relationships, but I don't expect you to know. But if you can prove them, that'd be great, right? Okay. Right, guys. So that's on the. So let me go back to just before I go. This is what I have done so far is for the bivariate case. So this is preliminaries for the bivariate. Bivariate case. Okay. So that's what I have done so far. There's no need for you to copy this because I will scan this and put them online after the class. Okay, the next thing, I'm going to consider preliminaries for the trivariate case. So these are preliminaries, one more time. This is for the trivariate case. Trivariate means three variables. Okay. All right, guys. All right, when you say a triplet, x1, x2, x3 has joint CDF, right? This means the following. This means that the so it means that the joint CDF is the joint probability that x1 is less than equal to x1, x2 less than equal to x2, and x3 less than equal to x3, right? So that's in the trivariate case, okay? Oh, by the way, I forgot to do something here. In the bivariate, can I go back to bivariate case just a minute before in the bivariate case, I forgot to say the joint PDF of x1, x2 is denoted by this is in the bivariate case, guys. Bivariate case, right? This is the notation for the joint PDF, right? And it can be obtained from the joint CDF by this, right? So what all you have to do is just differentiate the joint CDF with respect to x1 and x2, partial derivatives, right? You get the joint PDF, right? Another way to do that is as follows. Alright. It can also be obtained from the joint survival function, right? And again, you take partial derivatives with respect to x1 and x2. That will give you the joint PDF, right? Okay, I'm sorry about it. Just put it back here. Hopefully you can see this. Okay, let's carry on with this. So this is the definition of the joint CDF when you have three variables, a triplet. Okay. Now, the let me be okay. The marginal. The marginal CDFs are as follows. So F, this is the marginal CDF of x1, and this can be obtained from the joint CDF by putting everything to infinity except x1, right? Okay, and the marginal CDF of x2 can be obtained from the joint CDF by putting everything to infinity except for x2. Alright, and the marginal CDF of x3 can be obtained from the joint CDF by putting everything to infinity except for x3. Alright, so okay, so these are the definitions of the so this is the CDF for x1, x2, and x3. Right? Then the joint survival function joint survival function of x1, x2, x3 is denoted by f bar in the top and is defined to be just a minute, is defined as follows. Right, defined as the probability that x1 is greater than x1, x2 is greater than x2, and x3 is greater than x3. Okay. Right, so this is the definition of the joint survival function. When you have a triplet of variables, right? Okay, and so let me put this here. You can see this. Then the once again the the marginal the marginal survival functions of x1, x2, and x3 as follows. So the marginal survival function of f right. I mean, what this means, this, remember, this always means the probability that capital X1 is greater than little x1. That's by definition, right? This is the same as f bar okay. If anything not clear, please let me know, guys. I'm really want to help you guys. Alright. So to obtain the marginal survival functions, you put all the arguments equal to minus infinity, except for the argument that you're looking for, right? So for x1, you put x1, all the arguments except for x1. For x2, you put all arguments except for x2, and so on. Right? So this is so how you obtain the marginal survival functions. So now the relationships. I will give you a break. Just let me finish this. Then after this, I will give you a break. The relationships between f the relationship between f and f bar as follows, right? So let me first of all write down the relationship of f bar in terms of f. So it's gonna be f bar yeah. So this is gonna be 1 minus it's gonna take me a while, please minus All right. So this relationship, given you should know the marginal CDF of x1s of all the x1, x2, x3, and these bivariate pairs, and also this trivariate pair. Then you can use this formula to obtain the joint survival function of x1, x2, x3. Given the joint CDFs, you can get the joint survival function. Again, this is a complicated formula. I don't expect you to know how to prove this. But if you can prove it, that would be great. I mean, the second relationship is expressing f in terms of f bar, right? So it's gonna be like this. Alright, so these are the two relationships between f and f bar. The first relationship gives f bar in terms of f. The second gives f in terms of f bar. I know that's complicated, guys, but is that okay? You're right. Yeah. I mean, it's like I don't expect you to prove any of this. It just try to use. I mean, if I give you these formulas, I mean, I will do some examples later on. But if I give you these formulas, you should be able to use them, right? That's the thing. All right. One final thing before the break. I know all of you guys are looking forward to the break. The joint PDF. The joint PDF of X of the triplet is written like this. Right, and is equal to the triple derivative, so you have to differentiate 3 times. Right, this you can differentiate this joint CDF 3 times with respect to this to get the joint PDF. Or alternatively, you can differentiate the joint survival function 3 times but you have to add you have to multiply. After differentiating it, you need to multiply by a negative sign, right? So these two formulas are equivalent to each other. Either you differentiate the joint CDF or the joint survival function. In the latter case, you need to put a negative sign, right? All right, guys. So let's take a 10 minutes break now, and after that, after the break, I will continue with the general case, right? Because so far we've done the bivariate and the trivariate, right? General case. I'll do it after the break. Alright guys, sorry I haven't brought chocolates today. I'll bring it tomorrow. How are you? You know the quiz. You already done the quiz too?
Yeah.
Oh, you have done it? Okay, thank you. Oh, you haven't signed that? Ah, come on, you forgot. Yeah. No, that's because if you multiply 1 by this, you get probability n equal to n, right? And the sum of that from 1 to infinity is 1. You follow what I'm saying? Yeah, because this is sum of all probabilities. The sum of all the probabilities from n from 1 to infinity is 1. You have any questions? Yusuf, you okay? Are you guys, you have any questions? You guys have questions? Yes, you have a question? Because if 2 is greater than minus infinity, then that's a non-event because anything is greater than minus infinity. Anything. So if you put minus infinity here, then you can ignore the second event. Because x2 must always be greater than minus infinity. Right? So this will become the probability that x1 is greater than x1. You can ignore this event. Alright? So this guy here will become the probability that x1 is greater than x1. So you have 1 minus the probability x1 greater than x1, which is the CDF of x1. Because remember, the CDF of x1 is the probability that x1 is less than equal to x1. You probably understand. Let me explain it in more detail. The thing is, like this. We have 1 minus. Okay, like this. Yeah, you have this, right? Yeah. And this is 1 minus the probability that x1 is greater than x1, x2 is greater than minus infinity. But this is always true. This is always true. This event is always true. Yeah? Because anything is greater than minus infinity. Yeah? Okay? So this will become 1 minus the probability that x1 greater than x1. Right? And this is, because this is complement of this event, there must be the probability that x1. Yeah? And this by definition is the CDF of x1. Is that okay now? No? Still not okay? Negative infinity. That's because I wanted to put a negative infinity to get rid of this event. No? We follow this. Yeah. Because I wanted to put a negative infinity so that this event is always true. But anything is greater than minus infinity. Any variable must be greater than minus infinity. Because minus infinity is the smallest value in the world. You know? So you can get rid of this event if you put minus infinity. Yeah. Any other questions you have? Or is that the only one? Okay, thank you. You guys okay? Are you okay?
Yeah, I'll go over it tonight at home.
Come and see me tomorrow.
我有2箱干嘛呀？拿过来干嘛？ 不是重要是正常2、3啊，一个箱子是装那个 T 的那个
Yeah, see never I noticed you gotta like
No, I mean,
是那个黑框眼镜，这儿是那个。不是，就是晚才的。没有，真没有。我真没有。我真没有。原来有。没有。
I guess that's because there's
就是普通黑框眼镜。
there's all like
叫普通黑框。
maybe there's some
没有近视。
我可是发现照片。
肯定没有。我之前有一次，但是你很久没有了。
头发染
不相信。
sometimes I'll go like like I feel like she likes me and
不要浪费我的日抛。
No. He just really
我给他发了我衣服，他没给我
I don't know, but like
I mean, if it's like
真是一波三折。
我真的服了，这什么鬼？
could be that.
流水其实不够，不够。怎么这帅？我其实跟我有仇。就我本来就是给他撞死。
Alright, any questions on? Hi guys, I'm back. Any questions on what I've done so far? Hello? Any questions? Anything? I know this is maybe a little bit complicated for some of you. Is that okay? Are you guys clarified any doubts you have? If you have some doubts, you can ask me now. You can ask me now. Any doubts you have? Yes. No. Right. All right. Now. All right. The next thing I want to do, listen, guys, please. the next thing I want to do is the general case which are called p-variates. So p can be any number, 2, 3, 4, up to infinity, right? Okay. So okay, suppose you have a random vector x1 to xp that has a joint CDF. This means the following. It means that this guy here, which is the joint CDF, is equal to the probability that x1 is less than or equal to x1, and so on up to xp is less than or equal to xp. Alright, so what I have written down is the definition of the joint CDF in the p-variate case. So p can be any number, any integer number, of course. All right. So to obtain the marginal CDFs of x1 to xp, what you do is the following. So for example, to obtain the marginal CDF of x1, you put everything equal to infinity except for x1, right? That's how you do it, right? And to obtain the marginal CDF of xp, you put everything equal to infinity except for the last one. Okay. Alright, so this is how you get the marginal CDFs of x1 to xp from the joint CDF, right? Okay. Now the joint survival function of x1 to xp is defined as follows. It's defined as f bar, so you put a bar on top of f. That always means the joint survival of x1 to xp. And is defined as the probability is defined as this joint probability. Alright guys? Alright. Now let me show you how to obtain the marginal CDFs from the joint survival function. Right, that's the next thing I'm gonna talk about. Excuse me just a minute before I do it. Just a minute. Okay. The marginal. Okay. The next thing I'm going to talk about is the marginal. The marginal survival functions are as follows. So for example, the marginal survival function of x1, to obtain this, all you have to do is you write down the joint survival function, and you put, except for the first position, you put minus infinity in all the other positions. You will get the marginal survival function of x1. Okay, and so on for the last of the marginal survival functions. You will put minus infinity in every place except at the last place. Okay. So this is how you obtain the marginal survival function, right, from the joint survival. And the next thing is the relationship between the relationships, I guess. The relationships between f x1 to xp and f bar of x1 to xp. Alright, first of all, let me, as I did previously, let me first give you the relationship of f bar in terms of f. So okay, this will be equal to 1 minus plus okay, and so on up to the last term. The last term will be the following. It's a Okay. I know it looks pretty complicated, but is, as you can see on the right hand side, all you have is the joint CDF, and on this side, on the left hand side, you only have F bar. So what I have given you here, guys, is how to express F bar in terms of the joint CDFs. I know it's a series of terms. The first term is 1, the second term is simply the sum of the marginal CDF, I from 1 to p. The third term is the sum of the joint CDF of xi and xj summed over all numbers I less than j. So I goes from 1 to p, j goes from 1 to p, but I must be less than j. Alright, and so on. And the last term is this one. This is the last term. Right? Again, I don't expect you to know how to prove this, because it's not trivial, but it can be proved. And the second, this is the first relationship. The second relationship is F in terms of F bar. When I say I less than j, it means you are summing over I and j, but I must be less than j. So I goes from 1 to p, j goes from 1 to p, but I must be less than j. So this is plus. All right, these are the two relationships. So the first relationship gives you F bar in terms of F. The second relationship gives you F in terms of F bars. Right? Okay, I will do some examples later on. So don't be scared by the length of the expressions. I will do some I will try to do some examples later. If not today, maybe tomorrow. I will do some examples. Right? Right, now the final thing, I know I always try to do as many examples, but before I go to some examples, the joint PDF of x1 to xp is as follows. So once again, there are two representations for the joint PDF. The first one is as follows: is the partial derivatives p times, right? And you differentiate the joint Alright, this is one representation to get the joint PDF. The second representation is as follows. Okay. So you need to multiply by minus 1 to the power p if you're using the second representation, right? Okay guys, so this is all. Now I think it's time I do some examples because you will complain, I know. I know if I don't do some examples you'll be lost maybe. So let me do one example or maybe two, I don't know. The first example I'm going to do is as follows. Is example 1. Suppose x1, x2, right, has the joint Alright, so this is the example I'm going to do. Maybe I'll do. Is that okay? Right? Find the following. You guys okay or what? Alright, let's do number 1. F bar x1, what do you think this will be? So I'm asking you for the joint survival function of x1. What is that? Sorry. Can you see it now? It's equal to what? is equal, what do you put here? You put minus infinity, but in this case the lower end point is 0, so you put 0, not minus infinity, because the domain of the definition is greater than 0, right? So this would be, if you put x2 equal to 0 into this formula, what do you get? You get EF minus x1. Okay? Right? And similarly, zero comma x2, you get EF minus 3. All right. Okay, can somebody tell me what's the joint the CDF of x1? What will it be? Huh? Come on, guys. What's the CDF of x1? Huh? What's the relationship between the marginal CDF and the marginal survival function? They are what? If you add this to this, what do you get? This plus this will give you what? 1. So therefore, so this will be 1 minus. Yeah, is that okay? Is that correct? You understand? Because the marginal CDF, this one plus this one is equal to 1 by definition, right? So, okay. Okay, V. Alright, now this is where you're going to use the formula that I gave you a minute ago. You remember the formula, guys? You remember this formula that I gave you 1 minute ago? This one here. You remember this formula? This one. Yeah, this is the formula I gave you a few minutes ago, right? So this is gonna be, if you use this formula, guys, this will be 1 minus then plus yeah, you see what I've done? I have simply used this formula here, right, to get this, right? So it's 1 minus the survival this one here. 1 minus the survival function of x1 minus the survival function of x2 plus the joint survival function of x1 and x2. So that's what we get. Okay. Okay. Right, that's V. Now the last part is to find the joint density. To find the joint density, you can either use this or use, which one would you prefer, this one or this one? In this case, which one? Will you use this formula or this formula, and why? The bottom one, yeah, because this, you remember the f bar is simpler. For this example, the f bar is simpler, right? So you will use the bottom one. So you will use the bottom one, which is E I mean, both formulas are the same. So, I mean, depending on the example or the exercise, you will use one of the two, not whichever one is simpler you will use, right? So if you differentiate with respect to x2 first, you will get you will get the following: minus 1 plus theta x1 theta. Correct me if I'm wrong, I often make mistakes in my differentiation. Okay, this is what you get, right? Then you need to differentiate with respect to x1, right? So to differentiate with respect to x, you need to use the product rule, right? So it will be one plus theta x2 theta x1 x2, and then you should differentiate this with respect to x1. You get minus theta right. Alright, so this is, I'm sure all of you know how to do partial derivatives. So first you differentiate with respect to x2, that will give you this. Then you differentiate with respect to x1 to get this, right? You okay, guys? You tired? Some of you look tired, guys. Yeah. Alright, so this is example 1. I would try to do one more example. Well, maybe I will. Example 2. Maybe I will give this as a homework for you. You can do it overnight. Would you mind? I also feel tired. I don't know. guys, and I don't think I have time to do this today, but would you mind doing this tomorrow? Well, before the class tomorrow. Yeah. It shouldn't be difficult. Okay. And if you have any questions, just feel free to come and see me. And and also email me or Zoom me anytime, 24/7. Okay, it's fine with me. Fine. All right, guys. So see you tomorrow. I will bring some chocolates tomorrow.
哇